Now I want to invite Charles Morris, Head of Enterprise Data Science, Financial Services at Microsoft, and Ed Sandoval, our very own Senior Product Manager, AI and ML at Redis, to dive into how RedisFi Demo was built using Redis Vector Similarity Search and Microsoft Azure AI and ML services.
Hi everyone, I'd like to extend a warm welcome and thank you for joining us today for our Redis Day broadcast from New York. My name is Ed Sandoval and I'm a Senior Product Manager at Redis, where I focus on our AI and machine learning product line. If you watched our keynote session earlier today, you probably saw a demo featuring the new Vector Similarity Search capability in Redis. We use it to extract valuable information out of corporate filings submitted to the SEC. Today's session is a behind the scenes on how this demo was built by teams at both Microsoft and Redis. By the end of this session, you will get a good overview of the entire AI and machine learning pipeline that was used to build this demo. Today, I'm joined by Charles Morris. He's a head of enterprise data science for financial services at Microsoft. He will be covering the Azure ML infrastructure and services used to build this demo. I will be focusing on Redis's vector similarity technology. Both of us will share our insights from our collaboration and some of the key lessons learned. We hope you enjoy this session. Today, we'll start the session with an introduction to vector similarity and one of its key applications, semantic similarity. We'll then move to explain how we use semantic similarity to analyze SEC corporate filings. After that, we'll show you the demo and we will explain each of the components that were used in the development of it. We'll finish the session with a summary of the lessons learned by both Microsoft and Redis as we build this demo. In simple terms, vector similarity is a measure of how different or similar two or more vectors are. A vector is simply a list of numbers. With advances in AI and machine learning, almost any entity, be it a transaction, a user, an image, a sound, a long piece of text, a time series, or a graph, can be turned into a feature vector. This vector, also known as an embedding, captures the most essential features of that entity in a way that computers and databases can easily compare. There are multiple types of applications that can be powered by vector similarity. Similarity search is one of them. If you spot similarity in time series data, you could spot similar trading patterns, and that in turn can lead you to trading opportunities. Similarity of graphs could reveal connections between different set of actors. Similarity of transactions can power fraud detection and threat detection applications. Similarity of users and products could also power personal recommendations. One key application of vector similarity when applied to natural language data is semantic similarity. Think of it as the ability to compare the meaning of two sentences or paragraphs. But before you can build any semantic similarity app, you need two components. First, you need an AI machine learning model that turns these paragraphs or sentences into a vector representation, an embedding. You also need a database to store, index, and query these embeddings. Later in the presentation, Charles will cover all of the details about the entire AI and machine learning pipeline, the model, and the model serving infrastructure they use in this demo. On our side, we use vector similarity search capabilities in Redis Search 2.4 to turn Redis into an in-memory vector database. With these two components in place, we can now turn our attention to how they can be used to analyze SEC filing data. Corporate filings contain a wealth of information about a business. Major markets, opportunities, risk, details of competitors, and business expectations. For this demo, a team of data scientists from Microsoft took to the task of downloading thousands of SEC filings submitted over the last 5 years. They parsed each filing and extracted critical metadata about them, including the name of the company, the industry, the filing date, and even down to individual paragraphs. Each paragraph was run through a sentence embedder or sentence transformer model to obtain embeddings for each of those paragraphs. This resulted in over 2 million embeddings and their associated metadata. From that point onwards, a team from Redis was able to pick up the data, that is the embeddings, and the metadata load it into Redis hashes, and build the front-end application you're about to see. If you join us for the keynote session at Redis Day London, you may have seen RedisFi, a superb demo of a fintech app. It's a fully functional robo-advisor built entirely on Redis real-time platform. I encourage you to watch it on later. We added a research tab to the RedisFi app. And what it does is that it allows us to perform semantic similarity search over the SEC filing data. But before we start querying the data, let's take a look and familiarize ourselves with the data in Redis. Using Redis Insight, I can explore the content of this database. I can immediately see that there are more than 2 million keys already registered on this database. If I take a look at any of those keys, I can confirm that they are hashes, and each of these hashes represent a paragraph in a filing. There's a field that shows the paragraph. Further down, there'll be a field that represents the vector associated with this paragraph, but also there is additional information about this filing. So the company that it referred to, when it was accepted, when it was submitted, even the industry that that company belongs to. Now that we're familiar with the data, it's time to start sending queries into Redis. But before I do that, I'd like to show you a log of the application so you can get an understanding of what is happening behind the scenes. Let's get that going, and let's submit our first query. We're going to start with this one, concerns over protest. As you can see, I have two options. I can search using full text search or semantic search. I'm going to jump straight away into semantic search, and then I'll come back to full text search. When I do that, I immediately get results. I'm seeing the top 1,000 most semantically similar paragraphs and across all of those 2 million paragraphs. And if I check now at the logs, I can see that the last command executed was ftsearch. And ftsearch is a command you use to query data in hashes. Later in the presentation, I will be explaining in a little bit more detail what ftsearch does and some of the syntax that it uses. Now let me go back to the app and explain a little bit more what happened before we got to this query. The natural language query that you see in the search box needed to be transformed into an embedding. And in order to do that, the app sent the text to an Azure Machine Learning real-time endpoint. This endpoint was serving exactly the same model that was used to generate embeddings for the original paragraphs. And this allowed us to compare the semantic similarity of that query entered into the search box with all of the paragraphs in the database. Later on in the presentation, Charles will be providing more details about the real-time endpoint and the technology that was used to serve it. Now that we have a better understanding of how to turn a natural language query into a vector and then from there extract a list of semantically similar paragraphs from SEC filings, I want you to turn your attention to the results we're getting. For this query, a wide range of topics is being identified. Things like social unrest, political uncertainty, terrorism, boycotts, consumer reactions. All of these, to some degree, could be interpreted as similar to concerns over protest. One thing is clear: the term protest appears only 34 times across all of those 1,000 paragraphs. And the word concern another 77 times. So one thing is for sure, semantic similarity is already identifying potentially more useful and relevant results than lexical similarity does. To illustrate this point further, let's take a look at a full text search. If we perform a full text search for this phrase, unsurprisingly, we get 0 results. The word scary is very unlikely to be in any filing to the SEC. However, if we now turn this into a semantic search, we immediately see much better results. A number of situations, pandemic, legal, economic risk, start to come up. So the value of semantic search is clear. The last issue that I wanted to address in this demo is how to start identifying patterns based on semantic similarity data. And for this, I want to focus now on an issue that has been impacting the technology sector. Let's look a little bit more into the details. So, in order to build this pie chart, we queried the top 15,000 most semantically similar paragraphs in those SEC filings. And then we aggregated those results by company. The result is that these are the list of companies that are citing or appear to be citing the chip shortage issue in their filings. And the number that you see in parentheses is the number of semantically similar paragraphs in those filings. So as you can see, this list is very insightful. You get a list of companies across multiple sectors: technology, defense, automotive, semiconductors, and many others. It is only when you start aggregating the results returned by the semantic similarity search at the paragraph level that you start to see how an issue like chip shortages is affecting multiple companies. And from that, you can even extrapolate and look at the industries that are being more affected by this potential issue, at least as far as information in SEC filings go. Now, I would like to invite Charles to talk a little bit more about the Azure ML technology that was used in this demo. But first, Charles, why don't you tell us a little bit more about yourself, your role at Microsoft, and how this collaboration between Microsoft and Redis came about?
Hey everyone, like Ed said, I'm Charles Morris from the Microsoft Enterprise Data Science team. Really excited to be here and talk to you about how we built this app in such a short period of time. And I think it would be really cool to actually go through how this came about and how our teams actually came together to build it, because I think there's a lot of really valuable lessons for our customers in how they're going to operate in their own environments. So I got an email from Pascal Ballard, who did the keynote earlier, saying, hey, the Redis team is working on this vector similarity search, and they want to partner with you to build out a demo in anticipation of RedisDays. And I said, great, that sounds really cool. Vector similarity search is a really cool area, and I haven't seen a lot of good implementations of it. So ultimately we came together, and the Redis team had already done a bit of work with news, and we actually had been doing in parallel some work on SEC filings. So we said, why don't we use that? So what was really cool was my team was able to work with the Redis team, and we were able to build and deploy these models through Azure ML and have a really cool handoff point that was an easy transition to the Redis team where they could pick up our predictions and our endpoints and easily integrate them into the app. And where this comes really handy is a lot of times in organizations, data science teams know how to build models, but they struggle when it comes to integration with other environments, especially for a complex use case like vector similarity search. In enterprise data science teams, there's often this handoff that happens between data science teams and data engineering teams and app integration teams. And the less clear those boundaries are, the harder and longer it takes to get these models in production, particularly for cases like vector similarity search. So what we were really impressed by as we were building this demo was just how easy it was to have this clean handoff point. So let's jump into how this was actually built. So at the base of this is obviously is Redis' new vector similarity search as part of their search add-on. So what we wanted to do was figure out how do we hydrate that search, but also how do we create a real-time embedding endpoint so that we can embed the queries and search against that Redis search. So we used Azure ML to build and deploy these models. And basically what we did is we had a Spark pipeline to ingest all the SEC filings data, But then from there, we are able to register the model in the Azure ML model registry and deploy it to both batch and real-time endpoints. Once we had all that data, we were able to dump the batch embeddings into Redis, where it was available for lookup, and then we were able to export the real-time endpoint to the Redis team so that they could call those in real time and get real-time encodings and look up against those backfilled embeddings. So with Azure ML, we have this really powerful tool for pro data science teams to be able to go in and create models, register them and track them and make sure they're keeping lineage throughout the process, and then be able to expose those models as production-ready endpoints for their downstream teams to pick up and integrate into the APIs. And the way this worked with the Redis team was we only had to have a few hands-on collaboration sessions where we were defining the specs between what we were going to provide from the model side and what Redis was expecting from the embedding search side. And we were able to work in parallel streams very effectively. And you have two teams who had never worked together, never met each other before. We were able to build this demo in a short time on top of juggling our day jobs of working with customers. So really excited to kind of dive in now and show you some of the pieces that made this possible. All right, so now to build and deploy these models, I'm going to jump into my Azure Machine Learning Studio and actually start to work with some of these models. So I'm going to go into my notebooks page where I've done some of the coding for this, and I'm going to go ahead and look through and work with the data sets and understand what we're doing. So I go ahead and I've imported the data sets that I've registered in Azure ML that are sitting in my storage account, and I'm pulling those in and I'm looking at those. And as you see, what we've done is we've taken each paragraph and created its own row in the table with some additional metadata about where in the index those things are found, so that we can actually take those and process them piecewise and embed for each paragraph, get an embedding back. So when it comes to sentence similarity and semantic search, it can be really hard to get ground truth because you don't often have a data set other than the standard benchmark data sets where you know what sentences and paragraphs are similar to each other. So in this case, we kind of took a guess and check approach and we tried several existing embedding models to see which ones returned good results. After some iteration, we realized that the all MP based net model was returning quite good results, and we were happy with it for the first iteration of our project. So we load that model from Hugging Face in the sentence transformers model, and we apply those embeddings to a sample of our paragraphs to make sure that it's working as expected. And in fact, we do get 45 embeddings, each with a dimension of 768. So now this is where Azure ML really starts to shine, is we need to not just be reliant on third-party hosted versions of the models. We want to actually make this enterprise ready and log them in our own enterprise model registry. And for this in Azure ML, we can use ML Flow with Azure ML as the model registry backend. So here you're seeing that we're using standard ML Flow code to register the MPNet model and log it in ML Flow and then register it. And then just as a sanity check, we're reloading it from the model registry and then running some embeddings to make sure that we're getting the results we expect to show that our model registration process was successful and that the model loads properly. And as you can see, in this case, we used a different data set. So we have 93 embeddings, each with the same amount of dimensions as before. So now if I go and actually look at the model that I've registered, you can see that I have several versions of the model, and each time I'm incrementing the version counter. Each one of these runs is associated with a run ID, so I can understand always what run happened with the snapshots and relevant linking that created that model. So I always have an audit trail of what's going on. I can click into this and I can see all sorts of metadata about the model. And I can also see the artifacts, including the model itself, as well as the ML Flow definition. I can also go back and see all the different versions of my model through time. But in this case, what I'm interested in is right here, you see that there's a deploy button. And what's really interesting about this is when I build my models and deploy them through ML Flow, I can do a no-code deployment of both real-time and batch endpoint APIs. So like I said, going back to our use case, we need both of these endpoints for this embedder. We need the batch endpoint so that we can score all the incoming SEC filings and load those embeddings into the Redis database. But we also need a real-time endpoint so that as users are writing live queries interactively, we can embed those and do the comparisons to retrieve the relevant documents. So I've actually already gone ahead and deployed both a real-time and a batch endpoint. So For example, here you can see that there's the batch SEC paragraph embeddings, and it keeps track of the model that I use as well as the compute I'm planning on using to run it. But in this case, I'm going to hone in onto the real-time endpoints. And you see here I have an MPNet embedder endpoint here. Now this is what we were able to share with the Redis team so that their application can make these embedding calls live. So you'll see that when you deploy through Azure ML, you get both a Swagger URI as well as a REST endpoint. So we were able to give this to Redis development team, and they're able to instantly use this. I can come in here and test my endpoint to make sure that everything is working as I expect it to. So I will just give it a sample span, where I will say this is a short span. And then I can send this to the model to make sure that it's working. And in this case, we have a 700 plus embedding vector. So if we actually go into here, we can see that the embeddings that come out of here are what we expect, and there's 769 rows. Of course, this is not that interesting by itself, and this is where the Redis Similarity Search really starts to take off. So what we essentially did at this point was we gave the code to call this model, which is auto-generated by Azure ML, and we're able to give this to the Redis team, and then Adi was able to integrate this into the web app. So at this point, our job as data scientists is done. We've built our model, we've deployed them to robust managed endpoints where they can be called both in real time and batch, and we've provided both the embeddings and the model endpoints to the Redis team. So now that the Redis team has everything they need for the application, both the real-time endpoints, the batch endpoints, as well as all the embeddings sitting in storage, they're able to hydrate their application and serve it to real users. I want to highlight how awesome this is that the ML team can really focus on the ML portion of this project, where we can actually go and build this, deploy these models, run through our MLOps processes, and then have a really clear point to integrate with the other teams. It was through this process that we were able to build this application so quickly, and two teams that had never worked with before were able to build this demo in a reasonable period of time. So now I'm going to hand it back to Ed, and he's going to walk you through what Redis is actually doing with these resources and how they integrate into the application for end users.
Thanks, Charles. With the batch and online endpoints in place, we had a way of generating embeddings for both the paragraphs in the filings and for any end user query entering the UI. We used the batch endpoint to generate embeddings during the initial mass loading of the paragraphs, or whenever the model was updated and we needed to upsert the embeddings. The real-time endpoint was used to generate embeddings at a low latency for any single end-user query entering the UI. Uploading the paragraphs, the embeddings, and the rest of the metadata in the filings into Redis hashes was relatively straightforward. Redis Search 2.4 ships with the right capabilities to make this task simple. With it, you can index and query vector data stored as blob in Redis hashes. You have a choice of two popular vector indexing methods. It also supports 3 distance metrics to compare the distance between vectors. And finally, one of the most exciting capabilities of Redis Search 2.4 is hybrid queries. With it, you can define a query that takes into consideration not only the vector, but also you can filter based on any of the hash fields indexed in Redis Search, any other field indexed, for example, as a geolocation, tag, text, or numeric. So this allowed us to create a semantic search based on the similarity of the paragraph, but also limited to a particular company or limited to a particular period of time. All of vector similarity search capabilities in Redis were implemented as extensions to Redis Search 2.4. In particular, the ftcreate command was extended to support 2 popular vector indexing methods, a flat index and an HNSW index. In a flat index, when you submit a query to it, your query vector will be compared against all other vectors in the index. In contrast, in HNSW, it uses an algorithm to approximate the response. In this algorithm, you have parameters that can provide you a trade-off between speed and accuracy of the results. In the snippet of code that you see below, you can see an example of how we use ftcreate to generate an HNSW index for the paragraph embedding. there are additional fields in the hash that were indexed: the company name, the file, the year of the submission, and even the content of the paragraph, just as a text. The FT search command was extended to support pure vector and hybrid queries. These are queries combining vector similarity with filtering on any field that has previously been indexed as text, tag, numeric, or geolocation. In the code snippet in front of you, you see an example of the new extensions to FT search. Anything left of the arrow is filtering criteria. In this case, we're looking for filings submitted in the year 2021. On the right side of the arrow is a semantic or vector similarity query. In this case, we're asking for the algorithm to return the k most similar elements to the query vector. And in this case, k is equal to 1000, as you can see in the parameters. We wanted to close this session by sharing some of the lessons that we learned during the process, but also some key observations and limitations that, unfortunately, due to time, we couldn't test. The first observation is that designing and building a semantic similarity search application was relatively straightforward. And it was largely in part because there was a clear separation of responsibilities from an end-to-end perspective. The data engineering team focused on extracting and parsing the filings. The data science team focused on experimentation, embedding generation, and ensuring the quality of the embeddings was good. From an MLOps perspective, it's all about deploying the model in a way that makes it simple for the app to send queries and for the data engineers to generate embeddings in batch. From a database perspective, the generation, the loading, and the searching of embeddings was made simple with Redis Search. And finally, the backend and front-end development was no different than any other application that requires database access. Some of the things that we ran out of time and we couldn't test, but we think would add a lot of value, is additional AI and cognitive services that Microsoft Azure provides. There are services like name entity recognition that could be applied to the paragraph in the filings to recognize people, places, or names of companies. And we think that this is important because it could help you form a better picture of how entities in a filing are located or are related to each other. Form Recognizer is one of those other technologies that could have probably made a difference. With it, we could have done better with data that was in table form in the filings. With Redis Search 2.4, I mentioned that the HNSW index has parameters that could configure that trade-off between recall and speed. We didn't have enough time to do this, but in a production environment, you would want to play with these parameters with your data set, make sure that you achieve the desired recall and throughput for your data set. And you will be pleased to know that this demo will be entirely open source. So please stay tuned for more announcements, and there will be another webinar which will go in a lot more detail than what we've gone through today. Before I go, I would like to remind you that Redis Search 2.4 is now available, and for anyone wanting to get their hands on, you can use Docker or Redis Stack. And finally, you can also try it out on a free subscription on Redis Enterprise Cloud. A big thank you to all Microsoft and Redis folks who were involved in the making of this demo. In particular, I'd like to call out Adi Wadasabi. He's the guy in the mask, and he is a demo wizard. He is a principal software architect at Redis and a superbly creative and resourceful developer. Devir Dukan, Alon Reshev, and Guy Avimore, who are the brains behind Redis's Vector Similarity Search, and Charles Morris and Jake Won from Microsoft. Their knowledge of data science and particularly applied to financial services, is incredible. Finally, big thank you to all of the sponsors and marketing teams on both sides. It was a real collaboration and a test to a strong partnership. Charles and I hope that you enjoyed this session, and please enjoy the rest of your Redis Day, New York. Back to you, Mike.
That was exciting, seeing how Redis Vector Similarity Search and Microsoft Azure technologies were deployed seamlessly to surface valuable insights from millions of paragraphs in SEC filing. We learned about vector similarity and some of its potential applications to the financial services sector. From semantic similarity to fraud detection, chatbots to spotting trade opportunities presented by similarities in time series or graph data, or just simply picking up trends from financial news articles or social media outlets, the potential is endless. Most importantly, the teams at Redis and Microsoft showed that modern software development organizations can adopt these disruptive technologies with ease.